So today I will talk about the symmetry-adapted Wannier functions. So before going into the symmetry-adapted Wannier function, let me first introduce the maximally localized Wannier functions. So by the way, do you see my pointer? All right, great. Okay, so basically what we get from the DFT calculation is the Brough state, and it is extended over the space. And what we want is this Wannier functions, which is localized in space. Then the transformation between the Brough state and the Wannier state is written by this formula. And here we have a unitary matrix U. And basically this is arbitrary, but we can uniquely determine this unitary matrix by minimizing the spread of the Wannier functions like this. But this is the idea of the maximally localized Wannier functions. But there is some problem if we want to make atomic centered Wannier functions. For example, the famous example is the case of the kappa, simple kappa. Then actually, if we put the initial projections with atom-centered s and d orbitals, then if we want to make the 6-orbital model, then the d orbital stay at the atom center, but the center of the s orbital deviate from the atom center. And this is because the so-called the max-loc, maximal localization procedure, does not care about the symmetry at all. Just they want to minimize the total spread. They do not care about symmetry. Okay. Then sometimes we want to make the symmetrized or symmetry-adapted Wannier function. And sometimes we want to make a really atom-centered Wannier functions, right? Then in 2013, there is a seminal paper by Ray Sakuma, which proposed a method to put some constraint, symmetry constraint on the maximally localization procedure. So basically what symmetry adapted Wannier function does is put symmetry constraint on the max-loc procedure. Then we can obtain the irreducible representations of the site symmetry group. Now this functionality is now available in the new version of the Wannier 90. But most importantly, please use the latest version, 3.1. Because in the version of 3.0, we have some bugs in the symmetry adapted mode. And it is fixed by Yonasan and Valerio. And I really appreciate their effort. So to avoid the bug in the symmetry adapted mode, please use the version 3.1. Okay. Then let me explain the technical word, the site symmetry group. So what the site symmetry group is? So it is the subgroup of the full symmetry group whose element leave the site position unchanged. For example, if we take the two-dimensional square lattice case, So in principle, in the crystal, we have a 3D-dimensional system, but for simplicity, let me consider the 2-dimensional model. Then in this case, we have in total, we have 16 symmetry operations. No, sorry, it is wrong. Sorry, it is in total, we have 8. So here 16 is typo. So we have 8 symmetry groups, 8 symmetry operations. And it consists of the rotation, like half pi rotation, pi rotation, 3 pi over 3 pi half rotation, and 2 pi rotations. And also, we also have the reflection symmetry about the x-axis and the y-axis, x-axis and y-axis. And also, we also have the reflection symmetry about the diagonal lines, like this direction and these directions. Okay. Then if we think about the side symmetry group at the 0, 0 position here, then in this case, all the symmetry operations, namely 8 symmetry operations, leave this position unchanged. So the multiplicity of this side is just 1. But if we think about the side symmetry at the 1/2 0 point here, then here we do not have the C4 rotational symmetry. If we rotate 90 degrees, then this side goes to 0, 1/2 by the 90 degrees rotation like this. So then in this case, the side symmetry group has 4 symmetry operations in total. And multiplicity of the side is 2. So basically the multiplicity is given by the number of the full symmetry operations divided by the number of symmetry operations in the side symmetry group. Okay. So here, this is the example for the kappa O2 plane in the famous Q-plate material. So here we have a kappa atom here and the oxygen atom here. And this oxygen and this oxygen are equivalent, yeah, because it is related by the 90 degrees rotations. And this is related to the multiplicity of these Wyckoff positions. Okay, then again, let me explain the concept of the symmetry-adapted Wannier functions in more naive way. So again, the symmetry-adapted Wannier function is given by the maximal localization procedure plus symmetry constraint, and we obtain the irreducible representations of the side symmetry group. Naively, we can understand the concept of symmetry-adapted Wannier functions using this figure. So in the maximally localized Wannier functions, we tried to find the global minimum of the spread from all possible unitary transformation, right? Then the maximally localized Wannier function will find the global minimum of the spread. But if we constrain the search space, which satisfy the symmetry property, namely the symmetry adapted unitary transformation, then within this space, we try to find the minimum of the spread. This is the symmetry adapted Wannier functions. So then if we think about this point in the full space, right? It might be the local minimum. Of course, sometimes, or in many cases, the maximally localized Wannier function agree with the symmetry of that adapted Wannier functions. But in some cases, it deviates from the maximally localized Wannier functions. Okay. Then let me explain the symmetry of adapted Wannier function in a little bit more detail. So basically, the problem is how to put constraint on the unitary matrix U. Then this is given by this formula. So the unitary transformation U for the irreducible K point should satisfy this formula. Okay, so basically in the symmetry adapted Wannier function, we try to obtain the unitary matrix only for the irreducible K point. This is natural because it is symmetry adapted. So we need to treat only the irreducible K point. Then we somehow symmetrize the unitary matrix using this D tilde matrix and this D matrix, the capital D matrix. And these matrices are related to symmetry. Yeah. And I will explain a little bit more detail later. Then the unitary matrix for other K point can be given by just by the information of irreducible K point. So here, this U of K is the unitary matrix for the irreducible K point. Then this U of RK is the general K point. So just from the irreducible K point information, we can reproduce the unitary matrix for other K point. Okay. So I forgot to explain. So here GK is the symmetry operation, which does not change the K point. Okay. So if we operate GK to the K point, it go back to the original K point. Okay. But this G gives the this G changed the K point. So this G give, if we operate this G to the irreducible K point, then this gives the general K point. Then in the symmetry adapted Wannier functions, the important quantities are these matrices, D tilde and capital D. Okay, then what, first let me explain the capital D matrix. The size is the given by the number of Wannier functions. And this gives the information how the symmetry adapted Wannier gauge block functions are transformed by the by applying the symmetry operations. Okay. So this psi k I is the index for the Wannier functions, and the k is the k point. And this is the symmetry-adapted Wannier gauge block function. This is what we want to obtain. And then if we operate the symmetry operations, then it is transformed in this way. And this D is specified, D indicate how the symmetry-adapted Wannier functions are transformed. On the other hand, this D tilde matrix, whose size is specified by the number of the bands. Okay. Then this is related to the transformation of the Kohn-Sham block functions by the symmetry operations. So the Kohn-Sham wave function is given by the usual DFT calculations. So here we have, for example, the random phase. It includes the random phase, okay? Random global phase, for example. Then if we operate this G matrix, then the Kohn-Sham wave functions are transformed in this way. And this d tilde is calculated numerically by applying the symmetry operation to the obtained Kohn-Sham wave functions. Okay. Then this d tilde and d matrix, the matrices are written in the new input file called DMM file. So this is the flow of the calculation of the symmetry adapted mode. So we assume that we have already performed in the case of quantum express case, we already performed the NSCF calculations and also the creating the .nnkp file by the pre-processing of the 1A90. Then what we do is first to execute the PW to 1A90, the interface from the quantum espresso to the 1A90. Then for this, we need the input pw21.in. Now, we have something. Is this symmetry adaptation needed? Yeah, in principle, even if we I don't know, the question is that is this symmetry adaptation needed for gamma only case? In principle, actually, I have never tried to create the Wannier function in the gamma only case. Because basically we need to create Wannier functions, we basically need the uniform K-mesh, right? Then we need to have the overlap between the K and K plus B. K plus B is the neighboring K point. And in the gamma only case, of course, we can transform the block function to the somehow the Wannier gauge, but and we can also do the symmetrization of this unitary matrix. But okay, let me answer this question afterwards. I need to think. Okay, so first thing we need to do is to perform the PW2 and for this we need the input PW21.in. And to perform the symmetry adapted mode, the modification to this file is very simple. Just put keyword write DMN and set it to true. Just this one line is enough to do the symmetry adapted mode. Then the PW2 will create the DMN file in addition to the usual AMN and MMN file. Additionally, it also creates the .sim file, which we will not use in 1A90, but it contains the information which symmetry operations are used to symmetrize this unitary matrix. Then for 1A90, of course, we need the input file like AMN and MMN. And in the case of symmetry adapted mode case, we have the we need the DMN. We also need the DMN input file. And also we also need this .win file, win file. Then again, the modification is very simple. Just put this keyword size symmetry to true. Then the 1A90 will create the symmetry adapted Wannier function. Okay. So this is basically how the symmetry adapted Wannier function works. Then again, the input quantity is this new file, the DMN file. And in this DMN file, the information of capital D and D tilde matrices are written. And let me give you the example of this D matrix. Okay. So let me give the example by using this material, calcium kappa O2. So this calcium kappa O2 is the famous family of the high TC cuprates. And it has a layered structure like this. So it is the quasi 2D material like this. So here the crystal structure is very simple. We have the kappa O2 plane and also the calcium layer here. So this blue one is the kappa and the red one is the oxygen. And this atom is calcium. Then in this material, in total, we have the 16 symmetry operations. And the space group is P4MMM. Then if we perform the band structure calculations, the band structure looks like this. So red one is the DFT band, and the blue one is the Wannier band. Okay, then let me try to make DP model. So DP model include one kappa D orbitals and 2 oxygen P orbitals. So to obtain the DP model, we put x square minus y square projection onto the kappa atom. And px to this oxygen and py to this oxygen. Okay. Then within this site symmetry, if we think about the site symmetry at the kappa site, in this case, the x squared minus y squared is the one-dimensional reducible representation, and the site multiplicity is here, just one. And if we think about this oxygen, the site multiplicity is 2. So this oxygen and these oxygens are equivalent. And if we think about the px projection, like pointing toward the x direction, like this, because here we do not have the C4 rotational symmetry within this site symmetry group, then the px is also the one-dimensional representation of this site symmetry group. Okay. Can we perform the symmetry? Yes. So the question. So now I had the questions. So the question is, can we perform the symmetry-adapted Wannier function calculation for any crystalline compound? Yes. Of course, the crystal do not have the symmetry. We cannot. There's no concept of symmetry adapted. But if it has finite number of symmetry operations, in principle, we can create the symmetry adapted Wannier functions. But of course, we need to be careful to choose the proper energy window. And yeah, let me explain this in the hands-on tutorial. And the second question is do the symmetry adapted Wannier function calculation take less computational time than the usual Wannier function calculations? It is, well, actually, I do not compare the computational time, but at least it does not increase the time too much. What we do is just symmetrize the unitary matrix for the irreducible K point. And in the PW2 we need to compute these D tilde and D, but it does not take too much time. So let's say the computation time is comparable to the usual maximally localized Wannier function calculations. Okay, then again, let me explain what this D matrix is. So D matrix is how does the symmetry adapted Wannier function transform by the symmetry operations. So it means that this px, like, for example, this px like function are transformed by symmetry operations, then how it is transformed. So this is the D matrix. And here we do not discuss D tilde matrix because it really depends on the random gauge of global phase of the constant wave function. So again, this D matrix is how the Wannier gauge symmetry adapted Bloch functions are transformed by the symmetry operations. Now I have the question, if the spread of the symmetry adapted Wannier function is less than the usual Wannier function, it is not. The global spread is always bigger or the same as the maximally localized Wannier functions. But if we look at the specific Wannier orbital, the spread can be smaller. I will give you an example later. Okay, so if we think about the Wannier gauge Bloch function at the gamma point, then this n is the index for the Wannier functions, Wannier gauge. And for example, if we think about the x square minus y square Wannier gauge Brough function at the gamma point, the Brough function looks like this. So here, this is just the repetition of the x square minus y square orbital. And in the case of px like Brough function, the Brough function looks like this at gamma point. And in the case of py case, it should look like this. Then, for example, if we focus on this Brough function, then if we apply the 90 degrees rotation, then it is rotated like this, right? So here we rotate 90 degrees like this. Then this Wannier function goes to this position. Then this agree with the py like Brough function at gamma point. So this looks the same, right? On the other hand, if we rotate this Brough function by 90 degrees, then this Wannier function, this amplitude goes to this point. Then after the 90 degrees, it looks like this picture. Then it gives the minus sign to this px like gamma Brough function. Okay. Then the D matrix is written like this. For example, if we apply the 90 degrees rotation to the Wannier gauge gamma point Brough function, then the x square minus y square orbital gives the get the minus sign like this. And here the px orbital goes to py, then the sign is 1. On the other hand, py orbital goes to the px orbital, then it has the minus sign. So this is a -1 here. So this is the D matrix here. Okay. And importantly, it is Brock diagonal for each irreducible representations. So x square minus y square orbital is the irreducible representation for this 0, 0 point. So the dimension is 1. And for example, this px, sorry, go back to this, right? So this px is the one-dimensional irreducible representation, but because we have the multiplicity of 2, then we have the 2 by 2 matrix here. Okay. So the Brock size is given by the dimension of irreducible representation times site multiplicity. Yeah, so the question, I had the question. So this D matrix depend on the initial guess. Of course, it depends on the initial guess. Then they obtain the symmetry-adapted Wannier function look like this. So here we have the x square minus y square orbitals and the px orbital on the oxygen and the py orbital on the oxygen. And these two px and py are equivalent. Yeah. So in this case, actually the symmetry-adapted Wannier function is the same as the maximally localized Wannier functions. Okay, then now actually we can apply this symmetry-adapted Wannier function to various. Yes, now I have another questions. So if the projections are not fit to the local symmetry, will do 1 in 90 give error. Yes, it gives the error. So if you have some mistake in the projection, then it gives error, and then you will see that your projection is wrong, or your Wannier window is not correct. Okay, then actually we can, if we apply to the symmetry adapted mode to the kappa, then for example, we can create the Wannier centered, atom centered S-like kappa orbital. We can also put S orbital at the interstitial site, like 1/2, 1/2, 1/2. Then we can also create the Wannier functions. And these two are not equivalent to, not the same as the maximally localized Wannier function. So the spread should be, total spread should be rather larger than the maximally localized Wannier function. Okay. Then here we show the final example to the application to the H3S. So you can also try H3S using the tutorial. So actually this H3S is the famous, now becoming famous for the record of the high TC superconductor under extremely high pressure. So usually this kind of composition cannot be a solid at the ambient pressure, but if we really compress the material, it crystallizes and it becomes solid. And then at extremely high pressure, it forms the BCC type crystal structure like this. And then if we do the band structure calculation for this H3S material, then the band structure looks like this. So black is the DFT band dispersion, and the red is the Wannier band. Then in this case, actually, we see a clear difference between the maximally localized Wannier functions and the symmetry-adapted Wannier functions. Okay, so here the crystal structure looks like this. Then if we put the, so we have one sulfur atom in the unit cell and 3 hydrogen atoms in the unit cell. And if we put symmetry, if we put the projection sulfur S, sulfur P, and sulfur D, and 3 s orbitals on the hydrogen, then if we create the maximally localized Wannier functions, actually you see that the Wannier center is not clean, and it deviates from the atom center. Also, the symmetry between the 3 hydrogen s orbitals are broken. In principle, these 3 hydrogen s orbitals should be equivalent if we think about the symmetry, but now the symmetry is broken. But if we do the symmetry adapted mode, then now you see the beautiful Wannier centers, right? Then, for example, the spread of the hydrogen s orbitals are equivalent among these 3 orbitals. Okay. Then if we look at the total spread here, it is around 10.93. And if we compare to the maximal locals Wannier function, the maximal locals Wannier function gives smaller total spread, 8.16. Okay. So this is because the off-diagonal part of the spread becomes smaller in this maximal locals Wannier function case. So off-diagonal spread is 1.6, but in the case of symmetry-adapted case, 4.3. Yeah. But again, as I already said, the total spread should be smaller or the same as the symmetry-adapted case. In this case, the total spread is smaller than the symmetry-adapted Wannier function. But if we look at the individual orbital, like hydrogen s orbital, then in this case, here the spread is 0.52, but in this symmetry-adapted mode, it is 0.50. So if we look at the individual spread, symmetry-adapted mode might give the smaller spread, but the total spread should be always larger. Sorry, okay, so I had the very general question: when or why should be the symmetry-adapted calculation performed? So the purpose of the symmetry-adapted Wannier functions. Okay, so there are various purpose, but one of the purpose is that one of the purpose to create Wannier function is to create the realistic tight binding Hamiltonian for the material. Then this is, for example, used in the calculating the topological property of the material. Or for example, in the case of strongly correlated material case, first we create the tight binding Hamiltonian, then using this tight binding Hamiltonian, we perform the, for example, the dynamical mean field theory calculations. In this case, it's sometimes helpful to help that if the tight binding Hamiltonian has proper symmetry. If the Wannier function deviate from the atom center and it is not normal atomic like, then the tight binding Hamiltonian will not have symmetry. So basically, in many cases, the purpose to create symmetry-adapted Wannier function is for using in the post-process calculations. Then another question is it possible to automatically generate Wannier functions? Yeah, is it possible to automatically generate Wannier symmetry-adapted Wannier functions? In principle, yes, if we can analyze the symmetry of the Bloch functions for the calculated cake point, then we can make it automatic. But for the moment, we need to put by ourselves. Yeah, thanks, Arash. Yeah, actually, if the symmetry is broken in the tight binding Hamiltonian, for example, we do not have a y point at the correct position. It gives the wrong. Yeah, for example, even in the case of Dirac point, it looks like it should have degenerate. The degeneracy might be wrong if the symmetry is broken. Yes, true. Yes. Okay, so now, okay, then now you can try the symmetry adapted Wannier function also using the tutorials example in the Wannier 19 package. So in the examples, we have example 21 and 22, and it is for, they are for symmetry adapted mode. And using this example, you can try the symmetry adapted Wannier functions. Again, please use the latest version 3.1 because the 3.0 has some bugs. Finally, what we need to be careful is that we need to have symmetry to get exactly atom-centered Wannier functions. For example, I sometimes have questions that they want to make the really atom-centered Wannier function for this molybdenum disulfur. So if we think about this monolayer material, then actually, so this is sulfur atom. So if we look at this sulfur, so in below sulfur, we have this molybdenum layer. But in the case of monolayer case, we have the vacuum in these directions. So there is no deflection symmetry with respect to this sulfur plane. Then, for example, the sulfur pz orbital cannot be, the position of the pz orbital of the sulfur should deviate from the atom center because we do not have symmetry, right? But of course, I mean, if we do, in this case, if we create the Wannier functions and plot in the real space, it looks like Wannier centered, no, atom centered. But if we look at the center in the standard output file, it should deviate from atom center. Okay. Okay, so I also have another question. Does symmetry adapted Wannier function works for lower dimensional material? Yeah, for example, this is the case of the two-dimensional material. So the monolayer molybdenum disulfur. And yes, you can apply the symmetry adapted mode. But again, sometimes if we put the vacuum layer, then the symmetry is lowered. Then again, as I said, the center of the sulfur pz orbital, for example, should deviate slightly from the atom center. Okay, to summarize, so this is the final slide. So again, so this is a picture of the symmetry adapted mode. So we constrain the search space. So we only search the minimum of the spread within this symmetry adapted unitary matrix space. Then sometimes it is different from the maximally localized Wannier functions. And for the future perspective, for the moment, for example, the symmetry adapted Wannier function does not support the frozen window or the inner window. And basically, it should be possible, but again, to create the symmetry adapted Wannier function, this window should be compatible with the symmetry. So this frozen window should be symmetry adapted. So we need to properly choose the frozen window. And for the moment, we do not support this frozen window. And also, yesterday I also had the question, and for the moment, we do not support the symmetry-adapted mode for the non-collinear case. And it is also an important thing to extend this symmetry-adapted mode to the non-collinear case. Okay, that's it. Thank you. So now I already had several questions, but now I can take questions. Okay, so the first question is, can we use the symmetry-adapted Wannier function in the strong spin-orbit coupling cases? So again, if we do the switch on the symmetry, spin-orbit coupling, then it becomes the non-collinear calculations. And for the moment, we do not support the symmetry-adapted mode for this. Sorry. The second question is it due to numerical or physical reasons that the symmetrized spread minimum is larger than the global minimum? The physical reason is that we restrict the searching space. So this space is always smaller than the all possible unitary transformations. Of course, sometimes this minimum can be the same as the global minimum. And in many cases, the maximum localized Wannier function is the same as the symmetry-adapted Wannier functions. But for example, in the case of the H3S case, clearly, because we restrict the searching space, the spread of the symmetry-adapted Wannier function is larger. And sorry. Okay, let's take the question from Alosh. Is it possible to automatically generate Wannier functions with enforced symmetry? Okay, yes, in principle it is possible, but for the moment we do not support this feature. What we should do is to analyze the symmetry of the Bloch function on the uniform K point within the window. Then with this information of this symmetry of the Bloch function, we can automatically create the symmetry-adapted Wannier function. Okay. Then the next question is, does symmetry-adapted Wannier function work without disentanglement? Yes. Usually, what I mean is that in the case of disentanglement case, we can have the different window for the outer window and the frozen window. But in the case of without disentanglement, the outer window and the inner window is basically the same, and in this case it works. So let's say the frozen window does not work for the disentanglement case. And the question from Kanshen, are there any difficulty about the implementation of symmetry-adapted? Yeah, yes, now the symmetry-adapted Wannier function also works for the disentanglement case. But what you cannot do is to put frozen window in this disentanglement calculation. Then the next question is, okay, suppose I'm trying to symmetrize tight binding model. First, I construct the capital D matrix for its basis, and next step would be to construct D matrix, which is okay, sorry, I'm not sure whether my pronunciation is correct or not. The question from Arkady, let me answer afterwards. I need to think more carefully. So the next questions, the two questions, can you comment on difference between minimizing constrained value centers? And the second one is, what about reality of the symmetry value functions? I mean, yeah, constraining value centers and symmetry-adapted Wannier functions. Actually, the idea is similar, but the way of implementation is different, and sometimes it gives the different Wannier functions. And actually, I'm not the expert on this, so if someone else is the expert for this, please answer for this question from Tommaso. The next question is, can we use collinear magnetism? I think it is collinear case, the upspin Brock function and downspin Brock functions separate. In this case, I think it should work, but I have never tried. So I think it should work, but if you want to do the symmetry adapted mode for the collinear case, please check it carefully. Sorry, maybe I missed the questions. There is a claim by Marianetti that constraining the center of the ring function. So there is a supplementary comment by Valerio. Yeah, there is a claim by Marianetti that constraining the centers of the Wannier functions automatically give you a Wannier function that satisfies the size symmetries. But this is an observation from a numerical experiment. Yeah, just constraining the center does not care about the shape of the Wannier function. So yeah, I agree. Basically, just constraining the atom center, just constraining the center, and it does not care about the shape of the Wannier function. But on the other hand, in the case of symmetry adapted mode, basically what we use the character table of the irreducible representation. So how D like Wannier orbitals are transformed by symmetry, or how P orbitals are transformed. So it also care about the shape of the Wannier function. Okay, thanks, Barry and Aro.